Hello friends, welcome back to the fast track revision course for GATE exam, and the subject running is control system. This is lecture number 5 of chapter 3, and the topics that we will cover in this lecture are steady state error and the constants related to that steady state error, which are position error constant, velocity error constant and acceleration error constant. We will see all these one by one. Let's start with the steady state error. So steady state error, what is meant by steady state error? Basically, first of all we will understand it. So steady state is basically the state when time is very large, means time tends to infinity, then that state of either input or any function will be called steady state because it has reached to its steady value. So in last classes we have seen that initially, if we are talking about suppose underdamped system, then in underdamped system the final output was to be unit step, means this was the reference input, and when we apply this reference input the output response used to be like this, means it goes first overshoots and then after the amplitude of the oscillation reduces as time increases and finally it settles down within some tolerance value. So for large time, for t tends to infinity, it becomes some constant, and that state is called steady state basically. Now what will be the error then? So in control system what we do, we apply some reference input and take some controlled output. So whatever the difference between the controlled output and the reference input will be called the error, and if we are talking about the steady state, then it will be called steady state error. So basically if suppose we have applied unity step input and the output becomes steady state, at steady state means t tends to infinity, the output becomes constant to some value 0.99 something. So whatever the difference will remain there, that will be called the error. So this way we can define the steady state as the difference between the input and the output for a prescribed input as t tends to infinity. So time will be taken as infinity and the difference between the input and the output will be taken, that will give the steady state error. And mathematically how we can define it? So mathematically we have defined as ESS represents steady state error, and as limit t tends to infinity, RT minus CT. RT is basically the reference input, this is input, and CT is the controlled output, this is output. So the difference between input and output taken at t tends to infinity, that will give steady state error. Now we from final value theorem in Laplace transform we already have studied it, that for any function if we want to find limit t tends to infinity yt for any function, then we can calculate it in s domain as well as limit s tends to 0 sys. So this way also we can calculate it. So this is final value theorem. The same I have done here, that in time domain we have limit t tends to infinity, then in s domain we can write it as limit s tends to 0 as, this s has been multiplied here as well, so as, and the Laplace transform of RT is RS, Laplace transform of CT is CS. So this way we can also calculate the steady state error. Now we define the transfer function of any system in Laplace transform, so this formula is more important than the above one, and let's see how we can find the steady state error for a unity feedback system. Suppose we have a unity negative feedback system like this. We have a forward gain G and there is unity feedback, means a feedback value is 1 and there is some junction at input side, and here the input is applied, that is R as reference input, and we have the controlled output, that is CS. Then overall transfer function of the system will be given as z upon 1 plus g. We have already studied it in the previous classes. So this is the overall transfer function. So CS, this CS will be given as RS into G into 1 G upon 1 plus G. The same I have written here, CS equals to RS into GS upon 1 plus GS. Now by putting this CS here and RS, the same RS here, and calculating it, we will get this result, that is ESS equals to limit s tends to 0 as RS upon 1 plus GS. So this is an important formula related to which we will solve it for the constant that we have to define. So let's solve it for the constant, that is position error constant first. So position error constant, here we will see, we just defined ESS equals to limit s tends to 0, check it again, limit s tends to 0 as Rs upon 1 plus Gs. We just defined this as the steady state error. Now we will apply the same formula to get the steady state error for unit step input. Suppose the input is unit step, it means Rs equals to 1 by s, correct? Because RT is UT, unit step, so in Laplace transform we can write Rs equals to 1 by s. Now ESS equals to limit s tends to 0, this is the formula, as Rs upon 1 plus G. So as instead of Rs we will put 1 by s and remaining will be the same. So 1 by 1 plus limit s tends to 0 Gs, because when we will apply the limit s tends to 0 in the entire system, so above numerator will be 1, so there will be no change, so 1 is represented the same way. Again this one will be represented in the same, because it is constant, we have not to put s anywhere. So variable is only in this part, so we will apply directly that limit to this Gs. So overall we can have this value means separately, and that separated value will be called the constant, that is position error constant. And so we can write the steady state error as 1 by 1 plus Kp, where Kp is a position error constant and that is defined as limit s tends to 0 Gs. So that's it. This is the derivation for the steady state error for unit step input. Means we had applied the unit step input Rt equals to Ut, and for that we have solved and got this position error constant. Now we will see, means we will apply the unit ramp input to get the velocity error constant. So let's see. So this is steady state error for unit ramp input. Suppose we have Rt equals to Tut. Again remember that formula, that of steady state error, limit s tends to 0 as Rs upon 1 plus Gs. So basically what we have to find that Rs, means the reference input. Once we will get that Rs, we will multiply, means we will put here in the formula of steady state error, and rest of thing we can do easily. So input is unit ramp, that is Tut, so converting it into Laplace transform we will get Rs equals to 1 upon s square. Now steady state error will be given as limit s tends to 0 s into 1 by s square, because we have got Rs is equals to 1 by s square and the remaining will be the same. Now when we will put this limit s tends to 0 here, we can see that easily 1s and 1s will be cancelled out, numerator will be 1, but in denominator we will get, means s will be multiplied with the entire system, so entire system will be the variable of s. So this will be limit s tends to 0 s into 1 plus Gs. Further if we put s equals to 0, then the first part will become automatically 0, so we will remain with the next only Gs, that is limit s tends to 0 s into Gs. So the same I have written here, Kv, means this entire denominator is called Kv, that is velocity error constant, and that can be defined as limit s tends to 0 s into 1 plus Gs. So when we will expand it and put s equals to 0, then that part will, means first part will be 0, so we will remain with the second part only, that is limit s tends to 0 s into Gs. So in last slide we see we just checked that what was position error constant. Let's see again. The position error constant is limit s tends to 0 Gs, and here we can see that velocity error constant is limit s tends to 0 s into Gs. So the basic difference between the two formula is, like here we are multiplying with s and there we are directly applying that limit. So when we talk about Gs, then it is same in the time domain as well, that is Gt. But when we talk about SGS, then in time domain we write it as dg upon dt, that is differentiation of g, and differentiation of anything will be like termed as velocity, and if we are trying to find any value directly, then that will be position of that value. So that's why it is called velocity error, because we are taking the limit, means steady state value for the differentiation of that gain, and earlier, for position error constant we are taking the limit of, means taking the steady state value of that position itself, so that gain itself. So that's why that was called position error constant, and it is called velocity error constant. And in position error constant, the final steady state error formula was ESS equals to 1 upon 1 plus Kp. We can see here 1 upon 1 plus Kp. But in velocity error, what is the formula? In velocity error, we can see that the formula is 1 upon Kv directly, because the one part has been already been 0. So there is some difference between the formula of a steady state error. For position error constant, 1 upon 1 plus Kp, that constant, and for velocity error 1 upon Kv. And Kp is what? Kp is just equal to the limit s tends to 0 gs itself, and for Kv limit s tends to 0 s into gs. So that these are the differences between these two. Now let's see. And position error constant was defined for the unit step input, and velocity error constant defined for unit ramp input. Let's see the last one, that is acceleration error constant. So for acceleration error constant or parabolic input, steady state error for parabolic input, so we have taken the parabolic input this way, rt equals to t square upon 2. So when we will convert it into Laplace transform, we will get rs upon equals to 1 upon sq. And later on, when we will calculate the steady state error, then we will apply the same formula, steady state error formula, that is limit s tends to 0 as rs upon 1 plus g. So same formula will be applied here, rs is 1 upon s cube, so put here, and finally we will get this result. So s square 1 plus s, or first part will be taken as 0, because limit, once we will put the limit, so first part will automatically become 0. We will remain with only limit s tends to 0, this part s square gs. So that will be called the acceleration error constant. So here we can see that we are taking the limit for s square into that gain. It means if we are talking about the time domain, then it will be equivalent to double differentiation of that gain, d to g upon dt square. So basically position error constant define that gain steady state value itself. Velocity error defines the differentiation of that gain steady state value, and finally the acceleration error constant defines the double differentiation of the steady state value of the double differentiation of that gain. So these are the differences between these constants, and why they are so called position error constant, velocity error constant, and acceleration error constant. Now the formula that we have to remember is steady, when we are talking about steady state error for velocity error and parabolic acceleration error, both we are seeing that 1 upon that constant will be the steady state error. But for position error constant, we have to remember that 1 upon 1 plus Kp was the formula. In case of velocity error, 1 upon Kv was the formula, and here we can see that 1 upon K is the formula. So acceleration error and velocity error are quite similar, but for position error, that one will remain there, because due to that limit s tends to 0 s, here for the last two cases the first part becomes 0, means 1 becomes 0 when multiplied with s. But in the case of Kp, position error constant, there was no s in multiplication with 1 plus Kp in denominator, that's why it remained. So overall we have finished these three constants. We have learned how it can be determined. So let's see some problems that has been asked related to these constants, means the concept behind this constants. So this is the question asked in 1998, 1 mark question. Consider a unity feedback control system. So I have already told you that all the constants that we have defined just now are applicable only when there is a unity negative feedback system. Otherwise, if there will be different feedback system or feedback system given for the control system, then we will see that case in the upcoming classes. But till now we have studied the velocity, all the constant, that is position error constant, velocity error constant, and acceleration error constant, all are defined for unity feedback system with some inputs, and the system forward gain was gs. And so we have calculated that steady state error formula as limit s tends to 0 as rs upon 1 plus gs. So that formula we will use here to get the different results. Okay, so consider a unity feedback control system with open loop transfer function this. So this is the forward gain or open loop transfer function. The steady state error for the system due to unit step input. So if we are talking about unit step, so it should come in our mind that unit step is related to the position error constant that we've studied in the first slide itself. So let's see the solution for this question. So this is a position error constant we have to find, and then we will find the steady state error. So position error constant, directly we will apply limit s tends to 0 gs, and then the value of gs is given as k upon s into s plus 1. So we have got infinity. Now finally steady state error will be written as the reciprocal of that kp, 1 upon 1 plus kp, but here is some constant written, a upon 1 plus kp, whatever it will be. So steady state error is finally 0. So this way we can calculate the steady state error for a unit step input. Now let's see one more question related to this concept. A unity feedback control system has open loop transfer, and again gs is given if the input to the system is unit ramp. So input is given unit ramp. So about what we are talking here, we are talking about velocity error constant. Once we will get the velocity error constant, that reciprocal of that will be the steady state error, or you can directly apply the formula as well. If steady state error is asked, then either you can solve it using this formula as well, limit s tends to 0 as r upon 1 plus g, and then put r as 1 by s square, but it will be so lengthy. So better you remember that formula, that for if we are talking about the unit ramp, it means velocity error constant we have to find, and finally for getting ess, we will apply this formula 1 upon kv. So let's find the velocity error constant first and then find the steady state error for this question. So here is the solution. The velocity error constant, of course, it will be given by limit s tends to 0 as z, as here written, but as is unity feedback, so it is of no use. Okay, so put the value of z for 1 plus 2s, this is the given value, and finally s tends to 0, so s will be put here 0, so we have got infinity. Again ess will be reciprocal of that kv and it will become 0. This way we have solved the questions related to the position error constant and velocity error constant. Acceleration error constant, I didn't find any question related to it in previous GATE exam, but it can be asked in near future, so get ready for that also. So these are the simple topics, and we will see some advanced concept related to these topics in the next class. Thank you so much for watching this video.